Hello and welcome to Special Relativity Part 4. Last time we derived gamma, which encompasses all departures from Newtonian mechanics into special relativity. However, the physical consequences of this, and really the new way of understanding the universe that emerges from it, is not really very transparent. The purpose of the rest of this series is therefore to uncrack the secrets which are hidden within gamma and really explore the fascinating implications of special relativity. Today, we're going to look at three of the most immediate physical consequences of special relativity: the abandonment of simultaneity, time dilation, and length contraction. Usually, these are often derived in very special physical situations. However, we're not going to do that today, and we're really going to do it in full generality. So, without further ado, here we go. We start today just after we left off last time. To take care of the constancy of the speed of light, we saw that the Galilean transformations, which take us from one observer of a constant velocity to another observer of a constant velocity, had to be modified to this. Furthermore, consistency of these two principles of special relativity further implies that the time coordinate between the two observers has to be modified as follows. If you didn't watch the last video, that's okay, but you'll just have to take these transformation laws between constant velocity observers as a given. From these two formulas, we derive the three effects that we mentioned in the beginning of the video. However, to really understand what's going on, we have to define them extremely precisely. And that's what we're going to do now. Let's start with simultaneity. The space spanned by the t and x directions, often called spacetime, consists of an infinite number of points, known as events. These events are intrinsic to the spacetime and really don't fundamentally change when we change our reference frame. For example, at one event, a muon might decay, and no change in reference frame is going to change the fact that the muon decay occupied that specific point in spacetime. Often, it's a good idea to take these spacetime points and group them into certain subcategories. Sometimes, the conditions that these groupings satisfy are invariant under a change in reference frame, and other times they're not. And actually, a lot of the counterintuitive aspects of special relativity originate from categorizations that are invariant under, say, Galilean transformations, but are really not invariant under these Lorentz transformations. This is all really abstract, so let's look at a concrete example. Let's choose a reference frame in which we're still, which remember we can absolutely always do, and choose a time t1. Now, we want to define a set of space-time points, or equivalently events, that belong to the simultaneous category. This is all space-time points, t1 and x for every single x in the space-time. And what does this do? Well, this traces a horizontal line in the plane. Two events are said to be simultaneous if they both belong to this set, and hence lie on the same horizontal line. Now that we've selected our simultaneous events, we can ask the question that we actually want to ask. Where do these events appear in another frame of reference that's related to this one by a Lorentz transformation? And we can totally answer this question. In our x and t coordinates, we define a set of simultaneous events at t1 to be t1 and x. How do the points t1 and x look from the perspective of someone that's moving to the right of us? We can plug them in for all possible values of x into our Lorentz transformations, and we see that the space-time events in the primed coordinates get occupied. Consider minus vx over c squared plus t1. We have one variable in x, and this is very similar to the equation y is equal to mx plus c for a straight line. Clearly the gradient is negative here, and it gets steeper when v becomes larger. Say x ranges from minus infinity to plus infinity. It's very clear that x prime is equal to x minus vt is also going to range from minus infinity to plus infinity. Putting the two together, we see that our simultaneous space-time points no longer satisfy the condition of being simultaneous space-time points in the new reference frame. And this is true regardless of what v is, so long as v is not 0. Therefore, simultaneity is not absolute, but depends on who the observer is. The simultaneous line rotates as the observer goes faster and faster away from us. Let's move on to the next effect, which in my opinion, and many other people's opinion, is probably one of the coolest effects of special relativity: time dilation. To understand this, again, we need to define exactly what we mean by a separation in time. Let's go back to our space-time diagram, and this time draw two simultaneous subsets of the space-time, one at t1 and another at t2. Two events are separated by a time of t2 minus t1 if one event belongs to the t1 line and another belongs to the t2 line. For example, take these 2 points. As this is our reference frame, and therefore we're not moving in space, for us we must choose an event from t2 and t1 at the same x point. For example, any one of the given following pairs will do. Equivalently, someone moving relative to us would define their own time separation identically, just with different coordinates. Time dilation appears when we ask the following question: what does the person moving relative to us, who uses the primed coordinates, think our time separation is? Specifically, we want to know what the difference in t primed coordinates is between the events that we've labelled t2x and t1x. Well, let's just simply plug this into our Lorentz transformations. But remember that from our perspective we're still, so x2 is equal to x1, and so the x-dependent terms actually cancel each other. This formula fully describes time dilation. Since gamma is greater than or equal to 1, and only 1 when the velocity is 0, from the perspective of the person moving relative to us, more time has passed for them than it has for us. Notice how very strangely we come to the exact same conclusion, but the other way around. Let's repeat this calculation from our perspective. Again, the x primes are going to have to cancel, because from their perspective, they're not moving either. And therefore this gives us this formula, which tells us that we see their time go more slowly than ours. This, however, must be true, or it would conflict with the principle of relativity. If the effect was different in one reference frame relative to the other, then this would privilege one of the reference frames over the other. Therefore, the effect must be the same for everyone. Summarising this, time ticks fastest for yourself. The third effect that we're going to look at today is length contraction. Here again, we have to be very careful and precisely define what we mean by length. To start with, let's go back to our simultaneous set of space-time points at some time t. The length of an object can only be defined in a meaningful way if the object consists of space-time points that lie on this line. In other words, we've got to measure both ends simultaneously. This is actually not really that obvious for an object that's still with respect to us, but is abundantly clear when we think about an object that's moving. Say we measure the back and then the front of this moving object. We get an answer that's larger than the object really is. Say we measure the front and then the back later. The measurement of the object is shorter than it really is. You can see that only if we measure the length of the object at simultaneous times, then we're going to get the same answer regardless if the object is moving away from us or not. A moment's thought reveals that something funny is going to happen in special relativity. If people disagree about which events are simultaneous, and simultaneously is so deeply ingrained into our conception of length, how can we possibly expect everyone to agree on length? Clearly we shouldn't. But let's now see this explicitly in a similar way to how we discovered time dilation. Consider the length between tx2 and tx1. What's the difference in x prime coordinates between these events? But again, t2 is equal to t1, and so therefore the t terms cancel and we're left with this. But now x2' and x1' are no longer simultaneous. We basically have to figure out the answer to this question. Which one was measured first, x1' or x2'? Using this formula, we see that because x2 is greater than x1, t1' must be greater than t2', and therefore the x2' measurement actually happened first. This means that they measured the back and then they measured the front, i.e. they must have over-measured it. We therefore need to correct for this effect and reduce the length by an overall factor given by this formula. Therefore, correcting for this, they measure that the difference in prime coordinates at a constant t' is given by this. But recall that gamma is equal to that, and so therefore we get a cancellation occurring, and therefore doing a proper measurement, the people moving to the right of us measure the length between the two space-time points to be given by this formula. Now, since 1 over gamma is always less than or equal to 1, therefore, in the primed frame, the length is less than in our frame. There we have it. These are the three most basic predictions of special relativity. Amazingly, they've all been confirmed to be correct at a remarkable experimental precision. People have been testing it now for over 100 years and haven't found anything wrong with the above equations. Whilst the way that we've arrived at these equations has been really rigorous, don't worry if it's not completely intuitive yet. At some point in the future, we're going to reinterpret what the Lorentz transformations really are in terms of space-time and gain a much more intuitive picture of what they're really doing to this space-time. Thank you all for watching.